Hello students. This video lecture will cover section 4.9, Antiderivatives. So this is our big transition from differentiation to integration. And so remember, the goal of differentiation is to find the derivative, or f prime, of a given function f. The reverse process, called antidifferentiation, is also equally important. Given a function f, we look for an antiderivative function, capital F here, whose derivative is lowercase f. In other words, we're looking for a function f such that when taking its derivative, we get the function that we're looking for. So here we can see the definition of an antiderivative. A function f is an antiderivative of f on an interval I, provided that f prime of x equals f of x for all x and I. In this section, we're going to actually revisit many of our derivative formulas in the previous chapters and write or discover our corresponding antiderivative formulas. Antidifferentiation is really about thinking backwards. So consider the derivative formula where taking the derivative of x, we get 1. What this does is it implies that the antiderivative of f equals 1. So we think to ourselves, well, what has a derivative of 1? Well, x has a derivative of 1. And because f prime of x equals f of x. And so using that same logic, we think, well, if I take the derivative of x squared, I get 2x. So the antiderivative of 2x should be x squared. And taking the derivative of sine, we get cosine. So an antiderivative of cosine of x should be sine of x. We can check that each of these proposed antiderivative formulas is true by showing that taking the derivative of capital F gives us lowercase f. So this brings up the immediate question, does each function have more than one antiderivative? And so to focus on this, we're going to look at that first example, f of x equals 1. We said that the antiderivative, or an antiderivative of that, is f of x equals x. Now because the derivative of a constant is 0, we can see that taking capital F of x to be x plus c is also an antiderivative of 1. Which is easy to check because here f prime of x is the derivative now with respect to x of x plus c. And that equals 1, which is what we wanted to end up with. So f of x equals 1 has an infinite number of antiderivatives. We have x plus any given constant. And so for that same reason, f of x equals x squared plus c is an antiderivative of 2x. And any function of the form f of x equals sine of x plus c is an antiderivative of cosine. And these capital C's here are to denote a constant. So if we let capital F be any antiderivative of f, then all the antiderivatives of f are of the form capital F plus c. So the only thing that we can do is add an arbitrary constant to that function. So while there may be an infinite number of antiderivatives for any given function, they all exist within a specific family. So here we can see that by changing the constant, we get all of the antiderivatives of f of x equals 1. And same thing over here, we can see all of the derivatives of g of x. So let's take a look at our first example. We want to find the antiderivatives. So remember here we're thinking backwards, so this 3 has to actually go up here. So we have to increase the exponent by 1. And so by doing that, the 2 would become a 3. So the 3 that would come down by taking the derivative actually goes away. So taking a look at our solution here, an antiderivative is x to the third. And you'll get a little bit better with this with practice. But you can see taking the derivative, the 3 would go down, and the exponent of 3 would become 2. So the complete family of antiderivatives is x cubed plus c, where c is a constant. Same thing with this function. We can write this as negative 9 times x to the negative 10th. And since the derivative of x to the negative 9th gives us negative 9x to the negative 10th, we can see that all the antiderivatives, the complete family, is x to the negative 9th plus c. Remembering that the derivative of cosine is negative sine, we're looking for a function whose derivative is sine. So we want to take the derivative of negative cosine in order to get sine. So the antiderivatives of sine are negative cosine of x plus c. So remember, we talked about the different ways to denote taking the derivative of f. In this case, the notation d dx of f means to take the derivative of f with respect to x. So it'd be nice to have notation to denote antidifferentiation. We'll get into this a little bit more in the next chapter, but the symbol used to denote the antiderivative is the indefinite integral. It's this long curly s. So this is read as take the indefinite integral of f of x with respect to x. The function is called the integrand, and for now the dx simply means that x is the independent variable or the variable of integration. So in this case we're going to say that we're going to integrate f of x with respect to x. And so here are all of the questions, the examples that we did in part 1 with the new notation. In addition, this lets us write the power rule for indefinite integrals. So you can see the integral of x to the p dx is x to the p plus 1 divided by p plus 1 plus an arbitrary constant. We have the constant multiple in some rules here, so the integral of a constant times a function with respect to x is equal to that constant times the integral of f of x dx. And the integral of a sum with respect to the independent variable is the sum of the integrals of their functions with respect to that variable. So in example 2, we're looking at some specific functions. So with part A, we have the integral of 3x to the 5th plus 2 minus 5x to the negative 3 halves with respect to x. So since we have a sum and difference here, we're going to split those up. So we're going to take the integral of the first term plus the integral of the second term minus the integral of the third term. The coefficients are going to come out. And then we're going to use the power rule on x to the 5th. So it's x to the 6th over 6. The integral of 1 dx is going to be x. And the integral of x to the negative 3 halves is going to be x to the negative 1 half over negative 1 half. Once the integration symbols go away, we always add the constant. And then the final step is to just simplify. For b, we're asked to find the integral of a quotient. So the first thing that we want to do in this case, since we can, is simplify. Then we're going to use the sum and constant multiple rules to separate into two integrals with coefficients out front. We're going to use the power rule for integration, and then simplify. One thing to note here is that the integral of a quotient is not just the integral of the top divided by the integral of the bottom. Finally, part C asks us to integrate a product. So where possible, we expand the integrand and then integrate each term individually. One of the major things to note with part C here is that the integral of a product is not necessarily the product of the integrals. This leads us to the indefinite integration of trig functions. So taking the derivative of cosine 3x, we use chain rule. So we have the derivative of cosine of 3x, which is negative sine of 3x, times the derivative of 3x, which is 3. So we can immediately write that the integral of negative 3 sine of 3x dx is cosine 3x plus c. If we factor the negative 3 out from this integral and divide it into both sides, we have that the integral of sine of 3x dx is negative 1/3 cosine of 3x plus c. Now this holds true if this 3 is any number besides 0. And we can do this for all of the trig functions, and that's how we result with table 4.9. The two questions in example 3 are direct applications of table 4.9. So here we let a equal 3 in result 3 of table 9, and we have that secant squared of 3x is going to be tangent of 3x over 3 plus c. If we let a equal 1/2 in result number 1, then cosine of x over 2 equals sine of x over 2 divided by 1/2, or 2 sine of x over 2 plus c. Table 4.9 is definitely something I would have available for the next test. So this gives us a nice bridge into an introduction to differential equations, which is a potential future course you might choose to take. If we know that the derivative of a function is 2x plus 10, then the differential equation is going to be x squared plus 10x plus c. Here there are an infinite number of solutions, all of which have this form. Now, if we consider a more general differential equation where f prime of x equals g of x, where g is given and f is unknown, the solution has to consist of antiderivatives of g, all of which involve some arbitrary constant. Usually, this is going to be accompanied by an initial condition that allows us to determine the value of that constant. So here we want to solve the initial value problem. F prime of x equals x squared minus 2x, where f of 1 is 1/3. So first, we know that the solution has to be an antiderivative of x squared minus 2x. So we antidifferentiate, and we get x to the third over 3 minus x squared plus c. This is by using the power rule and the difference rule. Here c is an arbitrary constant, so we have one solution that's a member of the family of functions. Now remember, that family of functions has some arbitrary constant that's being added to it. However, we have that initial condition that says that the value of the function at 1 is 1/3. So though we have found an infinite number of solutions, our particular solution has to go through the point 1, 1/3. So we take our general solution, x to the third over 3 minus x squared plus c, and force it to go through 1 for x and 1/3 for y. That allows us to solve for c, which in this case is 1. So this initial value problem has a solution of x to the third over 3 minus x squared plus 1. This initial value problem allows us to revisit some of the motion problems that we talked about previously. So if we suppose that an object moves along a line with a known velocity given by v of t for some time greater than 0, then its position can be found by solving the initial value problem. S prime of t equals v of t given s sub 0, which is the initial position, for time 0 in the position function. And we can do a similar thing with acceleration. So example 5 says that runner A begins at point s0 equals 0 and runs with velocity 2t. Runner B begins with a slight head start. Its position at 0 is at 8 and runs with a velocity of 2. Find the positions of the runners for t greater than 0 and determine who is ahead at t equals 6 time units. So here we allow runners A's position s of t with an initial position of 0 at 0. Then the position function satisfies this initial value problem. So since the derivative is 2t, we know that the position function is t squared plus some constant. Since we're going to substitute in 0 at 0, we find that that constant must be 0. So, position of runner A is given by t squared for all time greater than 0. And we work out the similar position for the initial value problem for runner B. We have s prime of t equals v of t equals 2. And at 8, we have the value, and at 0 we have the value 8. Since the derivative is 2, the position function is 2t plus a constant. Substituting in what we know, we get that c equals 8, so the position of runner B is given by 2t plus 8 for all time greater than 0. So here we have t squared, and here we have 2t plus 8. Now, as time travels, we can see that runner B has the advantage right up until time equals 4. That's when runner A actually catches up and passes them. So by t equals 6, runner A is ahead. Example 6 talks about motion with gravity. So, neglecting air resistance, the motion of an object moving vertically near Earth's surface is determined by the acceleration due to gravity, which is about 9.8 meters per second per second. If we throw a stone vertically upward at time equals 0, with a velocity of 40 meters per second, from the edge of a cliff that's 100 meters above a river, we want to find the velocity of the object for time greater than 0, find the position formula for the object, find the maximum height, and with what speed does the object strike the river. So our first goal is to set a coordinate system in which the positive axis points vertically with s equals 0 corresponding to the river. We want to let s of t be the position of the stone measured relative to the river for all time greater than 0. The initial velocity of the stone, or v of 0, is 40 meters per second, and the initial position of the stone is s of 0, which is 100 meters. Now, the acceleration due to gravity points in the negative direction, so the initial value problem governing motion is given as acceleration is the derivative of velocity with respect to time, and it's negative 9.8. And so our initial condition is v of 0 equals 40. The antiderivative of negative 9.8 is going to give us negative 9.8t plus some constant. Plugging in what we know about the initial velocity gives us that c is 40. So the velocity of the stone is negative 9.8t plus 40. So the velocity is going to decrease from its initial value until it reaches 0 at the highest point of the trajectory. And that's going to happen when this function is 0. Solving for that tells us that at t equals about 4.1, the velocity becomes 0. Now that we know the velocity of the stone, we can determine its position. So velocity is the derivative of the position function. So we have negative 9.8t plus 40 with this given initial condition. At 0, we are 100 feet above the river. So we take the antiderivatives of negative 9.8t plus 40 and get negative 4.9t squared plus 40t plus c. Our initial condition implies that c has to be 100. So the position function of the stone is shown here. Now, one thing to remember is that this position function is shown with respect to time. This is not trajectory, this is position. So again, the position function of the stone increases from 0 to 4.1 and decreases from about 4.1 until it hits the river surface at around 10 seconds. For t greater than 4.1, the position function decreases and the stone strikes the river when the position function reaches 0. Since we only care about roots of this equation that are positive, we find that around 10.2 seconds the stone hits the river. To calculate its speed in meters per second, we plug 10.2 into the velocity function and take the absolute value since speed is always positive. Plugging 10.2 into the velocity function, we find that the value is about negative 60. So the stone strikes the river at about 60 meters per second. That concludes section 4.9, Antiderivatives. And that concludes chapter 4. When we meet again, we'll start discussing chapter 5, which begins our discussion of integration.